This Google Meet session is being recorded. If you do not have permission to be recorded, please turn off your camera and microphone when the recording is in progress. You may not download the recording or in any way keep the recording, including taking screenshots or pictures or copying the video. You may not distribute any image depicting another student or staff member. Okay, now, so the plan today is just to look at this. Not that, that's from first year, Chem. You've seen all this. Or if you haven't, you will again when we go deeper. Okay, so Taj, what we're doing is we're just recording the show. And because so many people are out, I don't know whether they took a I'm sick of being at home day or whether they're in the protest or whatever. Okay, so here's the deal. We started yesterday. So quick review. We started yesterday with pressure versus being proportional to 1 over volume. All right.
You're drawing above the camera.
Above the camera. Thank you. No, I'm not. All right. Thank you. All right. And the bottom is there. Okay. Okay. Now, so pressure is proportional to 1 over volume. And we had to adjust the pressure such that we took into account the atmospheric pressure. In most cases, the thing we had to do here with the books will be totally irrelevant because most pressure gauges are here in the atmosphere and they don't start at 0 during atmosphere. Now you got to be careful with that because some places they actually use pressure gauges and they want to know what the pressure inside the tank is, and that would not account for atmospheric. All right. And for instance, if you have a tank like a I don't know, say a propane tank, your propane tank's not empty when it's empty. All right, your propane tank's not empty when it's empty because in point of fact, it's the same as when you breathe. You don't empty your lungs. Think about it. Okay, then what we did is we went on to say that pressure is proportional to temperature. And again, we had our situation where it didn't work out very prettily because we were using degrees Celsius. I'm not even sure if that's a word. But once we adjusted to Kelvin, everything worked fine. So if we slide the scale down so that Kelvin temperatures are what we use, we'll be perfectly okay. All right. So those are the 2 things that we worked with yesterday in terms of the labs. Now, or the video, excuse me, and the book lab. Now, other things, I mentioned yesterday, this is all review. If I have what's called a rigid container or a solid container, or, you know, something that says that this container cannot change volume, then the only things that are going to change within it are going to be the pressure. We can change the number of particles, we can change the temperature, but volume is going to be a constant. Now, important note, always, 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 the volume, when I use constant, it's not the same constant. If I throw K up there, I'm going to be throwing K all over the board in a minute, and those constants aren't the same constant, they're just a constant. So if we come over here and say P is equal to some constant 1 over V, and then later we say P is equal to some constant T, those are clearly not the same constant. It's not possible because this K is relating some pressure unit and a volume unit. This K is relating a pressure unit and a temperature unit. So they're not the same K, they're just a K, a constant. Okay? At any point, stop me. I don't know if I'll leave, whether the chat will actually make a noise. So if you chat and I don't acknowledge it, please voice in. All right. So if we're in a rigid container wherein volume doesn't change, we can change the number of particles. And as we said yesterday, the pressure is obviously proportional to the number of particles. If you put twice as much stuff in, if you'll remember from the video, the pressure was twice as much. Or in the thing, I think he had 2 flasks and he had it all in one flask, and then he separated it, and it was half an atmosphere in each flask. So pressure and number of particles directly proportional. If, on the other hand, we have a balloon, and the balloon is able to flex to meet the pressure of the air, then pressure is actually effectively held constant. Let me say that again. If the balloon is flexible, then the pressure is effectively held constant because the interior pressure of the balloon is always going to be the exterior pressure of the air, plus a little bit of pressure exerted by the elastic force of the balloon itself. So if that's the case, if we're working with a balloon, then volume is effectively always proportional to the number of particles. All right. Similarly, we've said pressure is proportional to temperature. We said number of particles is proportional to pressure. Number of particles is proportional to volume. If that, now, all of that is basically able to be used if we change one set of conditions at a time. All right, so let me show you something. I'm going to erase this, but you'll have a video so you can look at it anytime. All right, and I don't know what the timestamp is, or I'd give it to you right now. All right, now, trouble is I'll only have a little tiny whiteboard. I'm used to having like 20 foot of whiteboard. Okay, so here's the deal. Let's say I take, little Johnny has a balloon, and little Johnny is holding that balloon here on the surface of the earth. Okay, let's say the pressure here is 1 atmosphere, and the volume of the balloon is 2 liters. Let's keep it simple. Okay, little Johnny's walking along, little Johnny trips and falls, and little Johnny loses his balloon and it goes up into the atmosphere and changes shape. All right, let's say it goes so high up that the pressure is now 1/2 an atmosphere. Way the heck up there. What's the size of little Johnny's balloon? Well, it should seem obvious, but let's do the math. Pressure times volume equals a constant. So here on the Earth, 1 atmosphere times 2 liters equals the constant. So the constant effectively is 2 liter atmospheres. So then 2 liter atmospheres, or atmosphere liters, I don't care. So now, set of conditions number 2, this was here on Earth, set of conditions number 2, up there, the pressure times the volume is equal to 2 liter atmospheres. The pressure is now 1/2 an atmosphere, times the volume equals 2 liter atmospheres. Therefore, obviously, if you do the math, you're going to get the volume to be 2 divided by 1/2. Please be careful when you do that. All right, 2 liter atmospheres divided by 1/2 atmosphere, and so you're going to get 4 liters, and your balloon's going to get bigger. Okay, now a couple of thoughts on that. One, please, I'm going to constantly stress this. This unit is great for common sense checks. This is a common sense check. Pressure decreases, therefore volume should increase. So if you don't get something that's larger than 2 when the balloon is up high in the sky, then you probably did it wrong. Okay, now the second thing is, and here's where things get easier, is, and I don't know how much gas stuff you did in first year chem because I know some of you ran out of time. So here's the deal. If P1 V1 equals a constant, and as long as the temperature is not changing, all right, so there's no change, let's put it this way. Change in temperature equals 0, change in the number of moles equals 0, then this will be true that P1 V1 equals a constant and P2 V2 equals the same constant. Therefore, what we can do is simply say P1 V1 equals P2V2, R2D2, and you don't have to solve for K ever. Okay, this is mostly a mathematical review, but maybe it's pulling in some new points. All right, so stop me if there's anything doesn't make sense. Okay, now let's take all of this and put it together, and we'll go to a place that hopefully some of you have already gone. All right, so let's go back up, top of the page. Okay. Now, here's the deal. So we said pressure times volume, constant. Okay, that's as long as the number of moles, there's no change in the number of moles, and there's no change in the temperature. But we also said that pressure or volume are proportional to the number of moles. Therefore, the number of moles should be on the opposite side. So notice, if this were constant, the number of moles could be involved in that K, or we can change the number of moles, new constant, and say that it falls on the opposite side of the equation, because if N increases, then either pressure or volume or both will increase proportionally. And the same thing we said about temperature. Pressure is proportional to temperature, or volume is proportional to temperature, provided there is no change in the number of moles. So temperature should be on the opposite side of the equation as pressure and volume. So we've got pressure times volume equals yet another constant, thus. And those of you that got into it in first year chem should know this equation as PV equals nRT. And if you've already watched Don't Memorize the Gas Laws, you should have seen this. But that's from whence it was derived. And its usefulness is both here as one specific equation, and also to get rid of things and go back and be able to solve for things in parts, like he showed you in the video. If you haven't, I think that you've seen that video already, haven't you? Yeah, it was due today at the end of the day, so you may not have seen that yet. All right. So here's the deal. Here's the takeaway. Takeaway number one. This whole equation, as written, is for one gas at one set of conditions. In other words, one sample at one set of conditions. Okay, so if I know any three of these, I can solve for the fourth one. So, example, little Johnny has his little balloon, and little Johnny is, halfway up Mount Everest. So the pressure is 0.63 atmospheres, and the volume of his balloon at that height, we don't know, but the number of moles is 0.06, and the temperature there is freaking cold, so it's about whatever, 163, no, what would it be? Let's say it's 10 below zero, negative 10 Celsius. Okay, what we can do with that is, if we know the pressure, the number of moles, and the temperature, we can plug that into PivNert, and we can solve for the missing variable. Now, there are, on your green sheet, whatever color sheet you make it, if you look really closely, there are three gas constants, depending on the pressure. All right? So there are three ways we measure pressure. Okay? There are three ways we measure pressure. Okay? Pressure can be measured in atmospheres, which is just somebody said, hey, 1 atmosphere. It's about what it is here today at this room on this time. That's all it is. All right. It can be measured in millimeters of mercury, which we didn't get to in a discussion for another time. If you want me to really explain why they use millimeters of mercury, I can, because we never finished the drinking from a straw discussion. All right. We really should finish the drinking from a straw discussion, but I said I would keep it to a point today. So millimeters of mercury, and then there's the metric unit kilopascals. All right, metric units kilopascals. And 1 atmosphere is equal to 760 millimeters of mercury is equal to 101.3 kilopascals. These are all the same. They have the exact same meaning. That's an atmosphere, an air pressure. Okay. Now the R values associated with that. Here's the idea. These pressures, if you plug in at a given set of conditions, any set of conditions, all 4 variables, you'll get the same R. So let me say that again. Any set of conditions, every set of conditions for gases. If you plug in all 4 variables for that gas at that set of conditions, you get the same R. Okay. And those R values are something like this. It's on your sheet, but it's like 0.082, well, I always used 1. Liters, atmospheres, moles, Kelvin, over moles, Kelvin. For kilopascals, now notice they use a different number there. Okay, they use 62.36 torr. All right. No, shame on me. Stop. Don't write that down. Okay. It's 8.31. Sorry. Brain fart. Okay, 8.31. They use joules per mole Kelvin. Okay, but it's actually 8.31 kilopascals liters over moles Kelvin. Okay, so that's an important distinction. They use joules, metric unit. I'm going to put it back into its proper metric unit, kilopascals times liters, so that the math works better in Pivnerd. And I know this is a holy mess, and I apologize, but I don't have enough board space. Okay, and then the atmospheres one, fine, is 62.36, and they use another weird unit. They use torr in your green sheet or on your assignment sheet, torrs per liter mole Kelvin. All right, torr is after Torricelli, who came up with it, Miss Aim. Okay, so I'll rewrite this someplace neatly for tomorrow, but here's the idea. Atmospheres, 1 atmosphere is the same as 760 millimeters of mercury is the same as 101.3 kPa. The atmospheres, this is the R constant. This is the R constant for kPa. This is the R constant for millimeters of mercury. So again, if I have any one set of conditions, and I'll clean this up and push it out at the end, maybe let you guys go and I'll finish the video. One set of conditions, I use the whole Pivnerd. If I have only some of the conditions, though, I can cancel things out and still figure out what the relationship is without having to memorize any of the relationships. Okay. So I'll show you an example of that, and then I'll clean this up once I've let you guys go or let you ask questions. Okay, I've jabbered on for a good 10-15 minutes. Does anybody have any questions? Anything in the chat? No? Okay. Questions, problems, concerns? Okay. One last thing then. Let me show you what I'm talking about, and you'll see another example of it in the video. So, in reality, in reality, little Johnny's balloon isn't only affected by pressure when he lets go of it and flies up in the air. Okay? In reality, there's going to be multiple things going on. So here's little Johnny here at the ground, and he has his balloon. Falls down, lets his balloon go, it goes up here. Now in reality, we've got a 2-liter balloon at about 0.96 atmospheres and at about 20 degrees Celsius. When the balloon gets up here, I want to know the volume, but the temperature is now negative 20 degrees Celsius, and the pressure is now 0.76 atmospheres. Now, there's a lot to do there. First thing, for any of these proportions to work, you've got to change them to Kelvin. These proportions won't work. If one of them is positive and one of them is negative, you can't set them equal. It'll never work. So we change this to Kelvin. That's 293 Kelvin. All we got to do is add 273. Negative 20 degrees Celsius, so 253 Kelvin. Okay, now let me show you the last thing and I'll shut up. Okay, here's the trick. If we take PivNert, if you memorize that, nothing else, you'll be able to do any gas problem. So you look at this one and go, okay, what is and is not changing? As long as the balloon is not leaking, the moles are not changing. All right, the R is a constant by definition, so it's not changing. So I go PV equals some constant times T. Or I can say, okay, PV over T is equal to a constant. So the same PV over T that applies in this set of conditions will apply in this set of conditions. So I can say if this is condition 1, P1V1 over T1 equals a constant. But if that same constant is going to be equal to P2V2 over T2. And now it's just a plug and chug situation. Now we know all the conditions down here, so we can plug in 0.96 atmospheres, 2 liters, and 293 Kelvin is equal to 0.76 atmospheres times X over 253 Kelvin. Now, let's do a logic check. How much did the temperature change? Went down by a little bit, so therefore the volume should go down by a little bit. What happened to the pressure? The pressure went down by a little bit, so the volume should have gone up by a little bit since they're inversely proportional. So it should not change very much off of 2. So if we plug all that in, I don't know what we get, but it should increase the volume slightly.
I got 2.12.
Sounds about
if you
right.
use 3 significant figures. Sounds
about right. Okay, and so that makes logical sense because the balloon got colder, so it's going to shrink, but the balloon also was exposed to less pressure on the outside, therefore it's going to expand. Because it's going to expand until the two are equal. But this works for anything. So a simple example is if I walk inside a deep freeze with a balloon, what's going to happen to the size of the balloon? Like that. If the pressure is still the same and the number of particles are still the same. Also explains why sometimes a tank will explode because it's just too full. Well, I think that's enough, don't you? Okay, hold on 1 second. Let me take a look at you guys. Again, I apologize. Taj is already asleep. Good morning, Taj. All right. So anybody have any questions, problems, concerns? Okay. So all this will be is practice, practice, practice with these. If I look at your schedule, tomorrow the short class, we'll talk about the molar volume lab. So make sure you get a chance to pre-lab that. Okay. So it would be really great if you would pre-lab that before class. Fair enough? Thank you. Okay, so what I'm going to do is basically at the end of this video, I'm going to go through and sort that out so it doesn't look like a mill of a hess, but you don't need to stay to watch me do it. So if anybody has any questions, put them in the chat if you want to stick, and I'll stop recording and then put up a separate recording. Anybody think they're going to stick around? Okay. I apologize for the chaos today, but I will get this video out as soon as possible. Thanks. Bye-bye.
Bye. Have a good day.
You too.
Have a nice afternoon.
Oh, yeah, you too. You too.
I was gonna ask a quick question about the molar volume lab. I was nodding my head, but I realized my camera's off, so
Hold on one second.
yeah.